Alright, so this is a problem I made up where we're going to draw the Lewis structure, and even just for fun, we're going to figure out what the dipole moment of this thing is, or if it's polar at all. So the first thing you want to do, I think, with some of these Lewis structures, go ahead and, I think you can just go ahead and try drawing this the way it's written. So we're going to have nitrogen here at our end, on the left side, oxygen in the middle, and bromine on the right. So the first thing we do is figure out how many valence electrons these things have. We have 7 in bromine, in the neutral bromine, 6 in oxygen. That is not 7. How did I pass the first grade? And then here's 5 in nitrogen. And we're going to take 1 electron from each atom to make single bonds. So 1 electron from oxygen to bromine, and then 1 electron from both nitrogen and oxygen to make these bonds. And so now you have a Lewis structure formed with only single bonds. Alright, so oxygen had 6 before, but it used 2 of its electrons to make bonds, so not only has 4 lone pairs. Bromine had 7 before, and used 1 of them to make a bond, so it has 6 lone pairs now. And nitrogen used 1 to make a bond, and only has 2 lone pairs now on the end, because it had 2 lone pairs and a radical before. So we look at our molecule and let's see what's wrong with it. Bromine's cool. It's got its octet, 2468. Oxygen's cool. It's got its octet, but nitrogen is not happy. So to complete the octet, we're going to need to use electrons that we already have in the molecule, because adding any more electrons would be wrong, because there are only so many electrons as each of these neutral atoms have, because the original molecule was neutral, so it has charge 0. If this molecule had a charge, or did not have or had a positive or negative charge, we would take or add electrons to these neutral electron configurations up here before we even started drawing bonds. All right, so what we're going to do here is, the only way we see that nitrogen has 2, 4, 6 electrons, so it needs 2 more electrons to form an octet. And if we take one of the lone pairs of nitrogen and make a, or not nitrogen, but oxygen, and make a bond between nitrogen and oxygen, we can see that we can make an octet that satisfies both atoms. So we're going to go ahead and do that. And this is the structure we get. So we formed this bond, so there's a double bond in between nitrogen and oxygen, and we used one of the lone pairs on oxygen, so now it only has 1 lone pair. So now the last thing we do is calculate the formal charges for the entire molecule. So oxygen's positive 1, we know that for sure. It's got 3 bonds and the lone pair. And then nitrogen's actually going to have 6 electrons in the molecule, but it only has 5 in the neutral one, so it actually is a negative charge. So we look at this and we add up our formal charges, and we're like, all right, that's cool. Plus 1 minus 1 is 0, and this Lewis structure's charge matches the charge of the original molecule, which is 0. So, you know, that's cool. Looks like we're right. But then we think about what we've learned from general chemistry, and we get super picky, and we're like, that's odd. Oxygen is more electronegative than nitrogen, yet it has a positive charge while there's more electron density on nitrogen. That's bizarre. So maybe this isn't the right Lewis structure. So now what we're going to do is switch our central atom to be the more electronegative atom. So we're going to try drawing it this way. So back to the beginning, we've got our neutral oxygen with 6 valence electrons. We've got neutral nitrogen with 5, and the bromine with 7 again. And we're going to connect nitrogen to both of the side atoms. So 1 bond between these 2 atoms, and then we're going to use an electron from both the nitrogen and oxygen to make another bond. And now this is our Lewis structure. All right, so again, bromine is going to be cool. It's already got its octet. And all the fiddling around we have to do at this point has to do with nitrogen and oxygen. All right, so nitrogen had, let's see, 2 lone pairs and a radical before. So 5 valence electrons before, and then it made 2 bonds, so now it has only 3. And now oxygen had 6 before, and it made 1 bond, so now it only has 5 valence electrons. And you see that oxygen and nitrogen they don't have an even number of electrons, or let's see, I don't think they've completed their octet. So nitrogen's going to have what, 1, 2, 3, 4, 5, so that's definitely not 8. And this one's going to have 1, 2, 3, 4, 5, 6 valence electrons, if I can count. Oh, my bad. It's going to be 2, 4, 6, 7, right? Because each of these double bonds counts as 2 valence electrons, or each of these bonds. 2, 4, 6, 7 on the nitrogen, and then this one actually 2, 4, 6, 7 as well. So they both just need 1 more electron. So you're going to take these radicals basically and make a double bond using 1 of their electrons. And so your new Lewis structure is going to look like so this structure is the correct structure for nitrosyl bromide. And it's better because there's not a lot of localized charges. Like this one up here had the all the charges going around, and the nature of the charges on the type of atoms is what really set off an alarm for that structure. So every atom in here is neutral. So that's normally a sign of stability right there if everything's neutral, and you have an octet on every atom. And no one's really trying to fight over electrons that should be, or no one's really trying to fight over electrons and is winning that shouldn't be winning. So this is the correct structure. So now we're going to take a look at what the dipole moment of this thing would be. So just look at each set of atoms one at a time. And in between the nitrogen and the bromine, we have that nitrogen is more electronegative. And so it's going to have your partial negative charge in this bond. And then bromine is going to be your partial positive. And the dipole moment vector is going to go this way, pointing from bromine to nitrogen. And then in this bond, oxygen is more electronegative. So it's going to kind of have a partial negative charge if you're just looking at this bottom. And then the nitrogen will be partial positive. And then your dipole moment vector will go this way. And then these 2 vectors will add up accordingly. You have the one from bromine to nitrogen looking like that, and the one from oxygen or nitrogen to oxygen looking like that. So your resultant dipole moment vector is going to be kind of horizontal to the left. So this is your net dipole moment. I'm supposed to draw the crosses on these 2, aren't I? So your net dipole moment vector is going to look a lot like this. Maybe just slightly almost horizontal, not necessarily exactly horizontal, because it just has to do with the geometry of the molecule. And also, if you want to get super technical, the distance between these 2 atoms is going to be a lot longer because of, bromine being like a period 4 element, and its valence electrons are way far away from its nucleus. And this double bond is going to be a lot shorter than the single bond, because the attraction is stronger between these 2 atoms, and also because these are period 2 elements that have electron distributions closer to the nucleus and stuff like that. But technicalities like that shouldn't matter in an exam as long as you get this part right, just the general direction of the arrow, not necessarily even the size correct. You should be fine. But I hope this helped a little bit. I also wanted to say, if you ever have an arrangement of period 2 elements, like take the example on like the first worksheet ages ago. You have this arrangement of period 2 elements. All these are in the second period. your central atom is normally going to be the atom that is in minority here. So you see you got 3 oxygens and only one lonely little nitrogen. So it's probably going to be in the middle of all those oxygens. And all those oxygens are going to be fighting over its electrons. What is the charge of this thing? Is it really? Oh, I see. So there's your Lewis structure for that one, and I'll leave it up to you to see why that is true. If you want to go home and try that one. All right, good luck.